Hi, my name is Marco Kellner, and today I'm going to talk to you about Newton's second law of motion through a simple lab demonstration. Here we have Newton's second law of motion at its core. Force equals mass times acceleration. And now, I will prove to you this law using an example of constant velocity. I have filmed myself rolling a simple ball across a table. This basketball, after it's been released, it has no net forces and keeps rolling at a constant velocity across the table until it falls off the table. This is showing constant velocity because the ball is not accelerating, therefore it has no forces acting on it, making it go faster or slower. Using an application downloaded from the internet called Tracker, I was capable of analyzing the ball's motion frame by frame. As you can see, I placed an XY grid and I tilted it slightly to match the x-axis along the path of the ball, for simplicity's sake. In this experiment, it doesn't really matter which direction the ball is rolling. Even if it rolls in negative x direction, the spatial displacement versus time is still the same. This is still true with the tilting the xy axis in this case. The reason why I am only tracking part of the video and not including when I throw the ball is because my hands are putting the initial force that makes the ball start moving. In this experiment, we are only interested in the part where the ball is already moving without any additional force. Knowing all this, now we can move on and see what Tracker has analyzed for us. On the bottom right side, it has logged the ball's position versus time in an Excel chart. We can copy this information for later. After having done the real-world experiment, we can move on to the simulation part of this lab. We are going to use Visual Python programming for this. Here, I am showing you the coding I used to simulate the experiment. The first lines of code sets the environment, or setting, for the module. The second section of the code sets the properties of the module, such as the object's velocity, which we were able to determine before using Tracker. The third section of the code is what actually calculates or runs the module, and it is what we are most interested in. At the top, it says, while t is less than 1.4. This means the module will only run for 1.4 seconds, and I said it like this because that is how much time the Tracker analyzed the video for us. The next part is where Newton's second law comes in. Fnet, or net force, is set to equal to a vector of 0 because we know that constant velocity has 0 net force. The ball's actual velocity is set to equal ball.vel plus Fnet divided by ball.m times delta t. This is simply Newton's second law written in a way so that Visual Python will understand. The next line updates the ball's position with each change in time, and lastly, t equals t plus delta t is written so that t will be updated as well. When we run the module, we get this simulation. It is a bit hard to understand because there is nothing to compare it to, but that sphere has all the same physical properties as the basketball in the video. By running the simulation, Python gives us a linear graph that can be converted to another Excel chart. If we copy and paste it next to the Excel information that Tracker gave us earlier, we get this. We can make a line chart that graphs both the informations so that we can compare them easier. The information that Python gave us is the ideal situation, where friction and other imperfections are ignored. So when you compare my experiments with the virtual model, you can tell they don't match perfectly. This could be explained because of friction, and also because the person holding the camera was shaking a little bit, affecting the position of the ball in the Tracker application. Regardless, the two graphs are very closely matched, so the imperfections can be ignored. With this, I have proven to you Newton's second law by showing you and explaining constant velocity.